So we're into section 9, or I'm sorry, section 7, talking about I/O management. And I'm going to skip through pages that we've already seen. We've already seen the 7.1 page talking about the hardware overview, pointing out that we've got 2 node boards here that have their local memories, 2 chips to them, and they talk to a crossbow. Off on servinfo, there's a document that describes how to put in your XIO boards and things like that based upon the number of CPUs you have, and how to distribute your I/O loads across all these XIO boards. And then that crossbow is going off into a bridge that converts it into PCI buses, and then we put third-party vendor cards out there on those PCI buses. And it's not really showing it here, but VME buses are commonly used in a real-time environment or data acquisition environment, those sorts of things. Process control, too. Manufacturing control. And the second page, 7.2, we've already seen already, talking about the disk partitioning, the way it's broken out. This is a rather simple story. When you get into RAID devices, you've got a whole cluster of these sorts of things. But describing the volume header, a special partition on each disk, what it contains, and the partition table, and then print VTOC down below, printing out what that disk drive's partitions look like. And we've got an XLV partition, we've got a raw partition that could be used as a swap device. It's probably a root that we've got here. And another XLV partition, and then the volume header and a volume. And I'm not sure that I would like having my swap in the middle of the device. Again, the 2 XLVs might be user and root. They're doing that to isolate user and root from each other because homes are in /user, and we don't want to fill up the root file system. But I myself would try not to oversubscribe memory, make sure that I've got a lot of memory. Memory's pretty cheap nowadays. And switch that raw partition towards the, switch them around, just for a performance reason. Now when you open up a file, you get this offset pointer. We talked yesterday about how we have the system file table. And in fact, within the application, there was that file structure that the user could get to. So every time I open up a file, the file structure creates a buffer within my application. And we also set up the system file table entry, which points off to the inode. And within that system file table entry are pointers. They're showing here where they're positioning, byte positioning into the file. 3 different seeks that were done into this particular file. Well. And that the inode itself eventually breaks, we broke out the fields in there, including account ID, user, owner, that sort of thing. LS can print out a lot of the contents of the inode. But attached to the inode, then the data for could either contain the data or contain an extent list. And the extent list is just pointing to all the different pieces of the file that are out in the file system. So we've got an offset where the offset into the file is, the starting block out on disk, and then the number of blocks. And this is what I would consider a fragmented file. I got 3 pieces, 5 blocks a piece. You know, 3 different places out on the file system. Okay. And the extent descriptor contains an offset into the file, the starting block, and the number of blocks. Now we also talked about yesterday that we've got this file system buffer cache. All I/O in Irix goes through file system buffer cache by default. Rarely do I find Irix machines that actually have physical I/O except for things like file system backups or database engines, things like that. But in the compute type of market, a lot of these high performance applications on Craze, they traditionally did their I/O unformatted and bypassed file system buffer cache. And over the years in Unicode, we actually added a bypass into the cache saying if you do a large I/O request, don't put it through cache. And there's a system parameter in Unicode that says how big we set that. But it's exactly the opposite in Irix. Now this is one of the differences between a compute server that's doing lots of I/O like Nastran. A lot of these sites are running Nastran and they're bottlenecking on file system buffer cache. And they can't get their CPUs busy enough because as they put the Nastrans into the system, they all sit there on an I/O lock, sleeping. So one of the things that I expect we're going to see in the future is some sort of cache bypass mechanism. But right now, end users have to worry about that. Now what's the disadvantage if I bypass cache? I'm going to have to sectorize the data myself. I'm going to have to make sure that the request I send off to disk is going to fit into the geometry of that disk drive. And that takes CPU time to do all that. So you may be giving up I/O time, increasing your CPU time, but the trade-off is you're able to run more NAS trans, for example, on the system. File system buffer cache I/O is your slowest I/O. And there's a routine called bcopy that does the movement between user space and cache and that sort of thing. It has its own ceiling in terms of performance. So if you really want raw performance of these drives, you bypass file system buffer cache, which means you're doing raw or direct I/O. Okay, and you have to specify that on your open or your reads or writes. In Fortran, you can use the assign command to actually say make it raw I/O and bypass cache. But again, your service time is going to go up to do that blocking. So cache is excellent for an interactive environment where I'm constantly reusing my data and my data fits in cache. Whereas my data becomes bigger than cache, like a car crash or something like that, I'm constantly busting that cache, moving in more data than the cache can handle. And you're thrashing that. That's when you bypass cache, go to direct I/O, and then you set your stripe width to the application request size so that when it sends a request, it's able to fill up that data pipe and shove the data down to the disk drives and let the XLV software break it into step unit sizes, stripe unit chunks, and send it off to the individual disk drives in that stripe group. And XLV and XFS do not understand geometries of RAID devices that were put together underneath them. So when you use XLV, XFS understands the stripe geometry that you've put together with a bunch of IBMs and Seagates. But once you start putting together RAID cabinets behind it, FS tab now has an option to give you an opportunity to specify, here's my stripe unit size for this disk array I've put here, and here's the stripe width of this disk array. And then XFS can send requests off to it that are friendly to the geometry of that disk drive. But prior to 6.5, if you put RAIDs out there, it did not know what the friendly characteristics of that disk drive were. Okay. And that's the big thing about I/O, is it's just this well-formed, friendly I/O data movement. And you can either sectorize it in your user space or sectorize it in the kernel. Letting the kernel do it's fine if you're the only one on the system. But how many of you have printed a PostScript file and paused for a little bit as that PostScript file is going through file system buffer cache and bottlenecking your interactive environment? Okay, so if it were to bypass that, you'd still have control. There'd still be buffers there available for you, and the PostScript file could bypass that particular resource and not plug it up while you're trying to use the interactive workstation. And having used Indies for a couple of years, a lot of times the pauses are you're choking file system buffer cache. And we're going to take a look at some tools to look at that coming up. So standard reads and writes are all done through file system buffer cache. That's the way Unix has always been. It's just in history of running scientific applications on fast CPU craze, we were able to generate fast I/O loads and start choking up the I/O capacity of this file system buffer cache. Just like any resource, no matter how big you make it, somebody can abuse it. Okay. There's only so many buffers there. If I ask for more buffers than are there, then I've got a thrashing problem, and I have to start pushing things out to disk to try to find space for my file. So at the high level I/O, we're making system calls. So anybody remember how I look at those system calls? How can I tell if it's doing direct I/O or buffer cached I/O? What tool was I using for looking at system calls? PAR, the process activity report. And then with Irix view, I can actually see a little S on the graph for every system call, drag it down to a window and see what that actual system call was. Irix view will look at an entire PAR trace and tell you what kind of events were going on in it. So PAR tracks all those reads and writes. Okay, and you can look at the PAR and it'll tell you the file descriptor, it'll tell you the address in memory, and it'll tell you the number of bytes that you're moving. And if O_direct is on there, there's going to be additional arguments to the system call. Then you do a man on the system call name to figure out what those arguments are. Okay. So the kernel's sitting there with this cache. Its purpose is for reuse of data. The whole term cache says I'm keeping age information in that cache so that I can reuse the data. If I'm not reusing the data, there's no sense in using cache. Except for the delayed write, let the kernel sectorize it for me and let it worry about it, which is fine when I'm the only one asking it to do it. But the more people on the system, the more NASTRANs running, they all bottleneck on that particular resource. And this is the resource, even on Unicos at NASA Goddard, I was getting 20-minute waits on man pages. And it was one application that came in, took all the buffers on the system, and you waited 20 minutes to be able to get a buffer. And once these applications get buffers, the age, if they're fast CPU-bound applications, they can reuse their data over and over again and dominate that resource because it's the least recently used algorithm. And I'm not as fast as something tied to a CPU. I've got human think time slowing me down. No matter how fast I hit a carriage return, I can't keep up with CPUs that are busy with an application not tied to anything, going as fast as they can. At the low-level I/O then, we talked a little bit about the layers. The system call, based upon the type of call, is going to go into those three layers. We're either going to do the I/O management, which reads or writes, or we're going to go into the file system area for opens and directory makes and links and management of the control structures for that file system. And of course, there are two other ways to get these disk drives. One was bypassing cache, which is referred to as direct I/O. But the third one was just going straight to the devices as character devices, going through dev disk. If I copy something off of dev disk, I'm bypassing the system call interface, basically, treating it as a character device. But it all starts with reads and writes. In Fortran, the Fortran I/O libraries translate it to reads and writes. And unfortunately, there's a tool called Procstat in Unicos we don't have in Irix that tells me about the Fortran call side, to tell me how many Fortran calls, how many rewinds, things like that. So block devices are disk-type devices. They have a fixed transfer rate to 512-byte blocks. Anything that goes to them has to be blocked or sectorized. It has to be well-formed. And we'd like to understand the geometry of that device to get it as aligned and well-formed as possible, so that when we send it off there, it fits into the geometry and the kernel doesn't say, ooh, this is going to wreck my device. I'm going to have to push it through cache because you didn't know what you were doing. Then we have the device-independent calls, open, close, reads, and writes, that manipulate the data. And we're going to talk about different types of I/O. There's sequential and random. Sequential is typical in the NASTRAN environment where I've just got an array of data that I'm running through an algorithm, satellite, FFT programs, things like that. Whereas random I/O is more typical in the database market, in news servers, mail servers, where you've got lots of seeking going on into the file. Then we've got direct I/O, referred to as physical I/O, and in the Cray world we always called that raw I/O. And then buffered I/O is the standard cached I/O that we've been talking about. And lastly, there's synchronous and asynchronous. And by default, most I/O is synchronous right now. NASTRAN and all these applications are doing synchronous I/O. But when you get into things like Netscape, Netscape does asynchronous I/O. It's going to start off the transfer, but you still want control of certain things like your sliders and stuff. So it'll start off the I/O and then give you control back to do something. In the scientific market, we've always said synchronous is probably better if you don't have anything better to do. What good is sending off an I/O request and then sleeping, waiting to see what it's doing? If there's nothing to do in the meantime, it's typically synchronous. Okay. Asynchronous is going to increase your service time because now you got to spend more time checking to see, are you done, are you done, are you done? So your service time goes up to do that sort of thing. Now there was something in Unicos that I don't know that they're using in Irix yet, but it's called asynchronous double buffering. And basically I've got two buffers constantly filling up one. So I start off the I/O on one, process the other one, and asynchronous I/O allows me to at least keep one buffer filling and one buffer being processed. So I'm able to overlap the two. But again, that takes more CPU service time to manage the multiple buffers. There are a few more applications that are doing asynchronous I/O as they start multi-threading, but typically the HPC market is synchronous. Then to get to these devices, again, we've also got character devices. We've got variable transfer sizes, 1 byte to the memory size of the system. Certain devices, such as tape, are blocked for efficiency, such that when I write a tape, I put tape marks in it and do some blocking of it. But it's not required. Usually on the tapes, there's volume serial numbers, all kinds of things that are written onto the tape. We've got sequential I only, no seeking. Okay, we can't position into a byte device. Direct transfers only. We do not use system buffer cache when we're doing direct I/O. And by the way, database engines do a lot of character I/O. Why? Because system buffer cache can get plugged up by somebody. Network traffic, mail, anything. We want to stay out of a public cache. There are independent system calls, opens, close, reads, and writes. Doesn't seem to mention it here, but there's also IOCTL. IOCTL is a way to manipulate the devices and do various things as well. Yeah, I wrote it down on my list. Okay. So tape devices, CD-ROM devices, things like that, terminal devices are typical character devices. And again, you can get to a block device through a character interface. There's dev disk and there's dev R disk type of thing. Now, there's something new in the latest Unix. It's called a vnode or a virtual node. It's basically a structure around an inode that when you open the file, the vnode is going to figure out whether this file is local. It's file system independent and figure out whether it's a local file, NFS file. We used to have the shared file system in Unicos, while we still do. This is the mechanism used to say, no matter what the file system is, I've got a single pointer. And then as I go into the file system, I'll be calling file system specific routines to process it based upon the vnode structure. So we can have XFS file system, EFS, NFS, /proc. We can put on PC file systems, all those sorts of things. You can have soft windows running on your Irix workstation running a PC environment and be able to mount a floppy disk in your drive as a PC file system, for example. Attributes of the vnode, it's a structure that's in memory and it's active only when the file is in use. It never resides permanently on disk. It's basically not part of the metadata. It's destroyed as needed. And it's dynamically allocated from the memory pool. All operations on a file are done through the vnode and multiple users of the same file share a vnode.
Can I ask a question
Sure.
on that software? You said you can add, like if you have a Windows PC or a Windows disk or something, you can bring that up and stuff?
Yeah. Soft Windows is a way of bringing up a Windows environment, and then you can mount disk drives and stuff like that. They have to be formatted as an IBM drive and have IBM or DOS type of formats and stuff. But yeah. It was originally called File System Switch, FSS, but now they just call it Virtual File Systems. So you can have a variety of different file systems built out there. And Cray created SFS as one of them. DFS is another possibility. Okay, DOS, Apple, Macintosh, and the protocols are different, but you're still able to deliver the files. Okay.
Is this vnode something that's local to SGI Cray?
No, it comes out of standard Unix. Cray picked it up as well as SGI picked it up, but it's a Bell Labs original thing. But it's gone through a couple layers of redesign, and it was originally called the Common File System, CFS, and File System Switch. But these developers have to rename stuff every few years, and it became a virtual file system or a vnode concept. So it allows us to easily create sub-layers that are file system independent. Okay? So that's what a vnode is about. But it's going to point eventually to the inodes. It's how we get to the inodes and stuff. And then the low-level routines, you see, will be file system dependent. But at the upper level, there'll be a common file system interface to them, or a virtual file system interface. Okay. And I forgot to mention /proc is also treated as a virtual file system, a vnode. And it says inodes and vnodes have nothing in common. They're different structures, but you can find the inode off the vnode. Okay? And vnodes are not saved on disk, nothing like that. They're just as you reference the file. So this is just trying to show us that layering technique, and we're going to look at this file system type, and it's been referred to as the file system switch. And originally it was called the common file system interface. And then based upon the file system type, with XFS, we pull up XFS underscore routines. If it's EFS, there's EFS underscore type of routines. NFS has their routines, /proc has their routines, and there are other routines for other file systems that we support. DOS and Mac type of file systems that can be mounted. Okay. And so each one of these we're showing mounts and unmounts to do the operations on the file systems, and then there's also some vnode operations to do the opens and closes and reads and writes. Okay, but they all have a unique starting name to them, and we'll handle each file system separately. So these VSF operation pointers points for things that handle the operations like mounts and unmounts, and then the vnode operations are manipulation of the actual vnode or inode. And again, you get to the inode off of the structures that these routines are using. I don't know if it actually gives us a vnode structure here. No. So that's all we need to worry about right now. And some of the stuff I should jump off to OS view and show you a few things there as we get the time. Okay, now this is just trying to show us that we've got this file system buffer cache. Whenever I do reads and writes, by default everything goes through cache. Keep in mind Irix, or Unix in general, is designed for the interactive environment where we're constantly reusing data. These buffers help VI, they help man, okay, but they may or may not help large-scale I/O applications. Okay, database engines avoid them because of the problems that they can create. Okay. So file system buffer cache, by the way, has two things staged in it. It's got both file I/O and paging. Whenever vHand steals a page, it shoves it into this page cache. So we've got this big cache structure, and there's a certain number of buffers that we're going to take a look at here. There are only so many buffers out there. Anybody remember what I said was the default size of these buffers? 64 kbyte. And how do I drop them down if I need to make them smaller? FS tab. When I mount the file system, BIO size can make them smaller. This means, for example, if I'm doing hello moms and everybody's on one machine learning VI, you know, it'd be beneficial to me to go to smaller buffers if I'm not doing 64 kbyte transfers. Database engines, 4 kbyte. Drop it down, more buffers within the same memory footprint. More buffers, then nobody can take all the buffers as easily. Maximum is 600,000 buffers. Okay, that's the biggest that you can configure on your system. But if you don't drop the sizes down and you got a small memory, the kernel's going to come up and say, well, I've got to drop that down because I don't have enough space for 600,000 64 kbyte buffers, and it will resize it down on you and give you a warning. But if you drop the size of the buffers down, then you'd be able to fit them into memory again, have more buffers within the same memory footprint. Beneficial in the database markets and the small I/O, lots of little I/O markets. Trouble is in the compute markets, like at Navo, they mix them all into one file system. So they're doing standard sequential I/O, and then somebody comes along and does a ton of random I/O, lots of little all over the place, and it hurts each other. And we'll talk a little bit about that as we go along. They're dynamically allocated as needed. This file system buffer cache can grow and shrink, grow and shrink. You have systune parameters to control the ceiling and the floors of those. Okay, so you can set it to how big you want it to grow. You can set it to how far you want to push it down if it gets too big. If I'm on a news server, I'd like to have it big, and I'd like to have it all inodes because that's what I'm working with. Okay. So it says system cache is a method of speeding up access to data in the disk file systems. That depends upon reuse of the data. If I'm not reusing the data, I can abuse this resource and cause all kinds of problems. Now the data is a disk sector that's held in cache as long as possible, and it's aged. There's an age chain through here. And BuffView is a tool that can show you the age of that page. When was the last time it was referenced? And I'm seeing a lot of sites that are bottlenecking on these sorts of things. Now also there's this concept of page cache, and page cache is basically this concept of all of physical memory as a page cache. And page cache means that if I got this page out there and I have to take it off the free list, I can still get back to it. Remember we talked the other day that vHand is going to stuff pages into the kernel. Okay, so that's what this page cache is being used for. And then if I reuse the page, I don't have to go to disk to get it. I have an opportunity to grab it before it's going to be reused. And then out of page cache, there's what they call chunk cache, and chunk cache is for file I/O. Okay. So all physical pages in memory are considered part of page cache, and there's the structure called PFDAT that maintains this concept of a page cache. And it's shared by the memory system and file system buffer cache. And the file system buffer cache has this name called chunk cache because it's in 64 kbyte chunks. If the system's primarily performing file I/O, nearly all the page cache will be dedicated to caching file data. If it's a news server, I want it dedicated to inodes because you got a ton of those. Even with mail servers, you may want a lot of inodes. A recent study I had was running Oracle to avoid all the inodes. So every news item was read into Oracle and kept track of in Oracle structures rather than using inodes to keep track of them for performance advantages. And there's a parameter called nbuff that sets the maximum number of chunk cache buffers you can have. Okay, I have no problem on my workstation with upping it as big as I can get it on my workstation. Because if there's free available memory there, I want to take advantage of it when I print my PSs and things like that. However, if I'm running 2 or 3 Netscapes, I probably don't have much memory. Okay, memory goes rather quickly with some of the GUI types of tools. So a lot of these sites, in fact, there was an errata that went out that said set nbuff to 20,000, and that is creating a problem at Navo because they've got one application that comes along and takes 7,000 of their buffers. They run 3 copies of it and their system is dead interactively. Those 3 copies are getting very good performance of the system, but everyone else has been pushed out of cache and is now marooned because they can't reuse their data quick enough. Setting this number nbuff really depends upon the load of the system and the nature of the applications you're running there. Okay, so some applications may take lots of little buffers. The application that iteratively writes 1, 1, 1, just put it in a do loop, write a single byte, that's going to take 1 buffer, a 64 kbyte buffer to write 1 byte. And that's just going to chew away at your resources. You can abuse these systems rather quickly if you're doing that sort of stuff. You know, the old debug printf to print out that variable in a loop. Okay, so you can up the nbuff, and that's one that is often, that's probably the first systune parameter that customers are used to modifying both in Unicos and Irix. But in Unicos, we always said make it as small as possible because everything's bypassing cache. But in Irix, everything's defaulting into cache, and we end up having to set it as big as we can. So this V node is pointing into the file system buffer cache pointers, and there's what's called a buffer tree. And then the buffer tree is pointing off into the page frame data. PFDAT stands for page frame data. The older name for a page was a frame. So each one of these things would be considered a page frame rather than like a stack frame or something like that. Now the buffer size can be from 512 bytes to 64 kbytes, but that depends upon what's underneath it. The default is 64 kbytes. But if I've got like inodes and stuff like that, they're going to be smaller because inodes are allocated out of the structure as well. And again, BuffView is going to tell you all about this structure. So these buffers are used for I/O caching to achieve I/O performance on blocks that are reused, frequently reused, and they'll stay in cache. Buffers are variable length and allocated dynamically. As I need them, I go to a routine called get block. So I'm going to do a get block and say, get me a block from the kernel. And the kernel will be doing that as well for things like accounting data and security logs and things like that. Buffers are groups of memory pages. They're not necessarily contiguous, but when I allocate out of the pool, they do have to be contiguous. But when you get into directories and things like that, they may not be contiguous. And each group has a buffer header structure called a buff_t structure. And again, the range was 512 bytes to 64 kbytes. Some of us wish we could go bigger than 64 kbytes for NASTran and things like that. 16 megabyte transfers might be more appropriate. That way I can do a stripe transfer through cache and then let it match the stripe width of my file system. But by default, it's going to break it up into smaller pieces. 64 kbyte is the default. And they just picked that as the middle of the road. Now these buffers are ordered by a B-tree structure sorted by block number. And the number of buffers is configurable by nbuff, and it's monitored by buff_view. And hopefully buff_view is the next page. And I wish I had buff_view. In Unicos, I have to use crash, and there's a buff command within crash that will print out these structures. In Irix, I've got this new tool that I wish I had in Unicos called buff_view that visualizes the contents of those buffers, and we've used it a couple of times. So nbuff is the most commonly configured one. If I have it set to 0, it defaults to a percentage of memory. Most sites change it, and in fact, recently, this example is setting it to the bad one, 20,000. I say leave it alone unless you've got a reason to change it. 20,000 is too small. Now in Unicos, we can make it small because the size of this cache is static. I can't change it. But in Irix, I can grow and shrink as needed. So that's to my advantage. I can make it big, and if I don't have a memory pressure problem, it's to my advantage to use that memory for reuse of data. Now, this is the file called mtune kernel, but systune is what actually changes this parameter. And with systune, you can't go back to 0. What you have to do is edit the stune file, var sysgen stune, and comment out that line and then remake your kernel, and that will get you back to the default. Okay. But 20,000 is bad recommendation. And in fact, it has caused a couple of sites problems. And they just read in the manual, the installation bulletin, set it to this because somebody decided, oh, that's a good middle of the road number. So nbuff specifies the total number of buffer headers. I multiply that by 64 kbyte, and that is the largest that my cache can grow. So if I've got a customer that's complaining that cache is 64 gig on the system, I can look at nbuff, multiply by 64 kbyte, and see how big that is compared to what they have. And then they have to decide, well, do I want to do that? Remember the other day I threw workloads at and it pushed the kernel back down. That's the normal behavior that should happen, but it doesn't happen in 6.4. So a lot of customers are dropping the numbers down in 6.4 to prevent it from growing and not getting pushed back down. And these behaviors are breaking all the time because the developers are changing the behaviors, rewriting the code all the time. So we're going to see nbuff. Nbuff is the critical parameter, the first one that most sites go to configure. And here is buff_view. Now we've used buff_view before. In this example, buff_view is configured to have 20,000 buffers on the system. So I can't hold more pointers than 20,000 of these things. Okay. And in fact, at this site, temp is using 1,000 buffers for inodes. Looking at here, we've got the vnode number, but if it says system, that is metadata. That's your inodes, directory blocks, all that sort of information. Then we've got the name of the file. For example, I have a core file sitting in here, but if it's metadata, it has no name. Then I see the device that it's on. In this case, you can often pick up file systems, and I've got some NFS activity, some XFS activity, user people, and various devices, but I can usually pick up file systems like temp here, things like that. And then the next one says what type of file system is it, and it looks like with NFS they're getting some of the additional arguments of the device. It looks like there's a bug here. This is a brand new tool, so expect those sorts of things. And remember, I hit a bug yesterday where it just hung. So I'd see XFS, NFS, things like that there. And the next one now is the number of buffers. Okay, so out of my 20,000 buffers, I can see who's using them, or I should say what file is occupying those buffers, the space of them. Okay. And in this example, with the 20,000 buffers, there's 13,000 of them that are holding data. And I can't see all of them here. There are lots of little files. Okay, it's a big list. There is a batch option where I can dump the entire list off to a file. But in the curses tool, it crops it. So there's 13,000 data buffers there. Over here, there's 4,151 system buffers. And these are for your metadata, your file system control data, inodes, directory blocks, super blocks, all that sort of information. In fact, that's what's presently dominating the list here. And this is sorted by size and stuff here. Okay. So we see temp has got 1,000 buffers. There's an NFS file system mount that has 1,000 buffers. Looks like another NFS mount, another NFS mount. And these are mounted XFS, but for some reason, I'm not sure what soft/int is doing. It almost looks like there's a bug in something having overwritten onto a table or something in this example. So I'm going to ignore that. But after the number of buffers, we then see the size, how much space in that memory footprint is this particular file taking, and there are sort options. We can sort and change the way we're reporting this stuff. And then we've got delayed write. This is data that's been written into cache but not flushed to disk yet. This is dirty data. And then we've got pointers. Where have we been pointing into the file? What's the lowest address we've gone into the file, and what's the highest address we've gone in the file? I basically don't use those. They're not of much interest to me. These are the key things of interest to me. And the bottom line is, how many buffers are empty? And you also have to worry about fragmentation. You may still have buffers empty, but you need more buffers than are available, and they have to be contiguous. So you can get into fragmentation where even though you've got some empty buffers, there's still contention to find a contiguous piece within your cache. Okay. So my 20,000 buffers gets broken out. Data, empty, system, and the last one is inactive. And the inactive one was the data that hasn't been reused in the last 100 seconds by default. And there's a parameter called auto-up that controls how old can the data be before it goes from clean to dirty. Doesn't really show it up there, but to go from clean to dirty. Or I'm sorry, from dirty to clean. How old is the dirty data? Like 10 seconds by default, and then I have to flush it off to disk so that the file system has an accurate copy of it. But that same metric is also used then to move it from clean to inactive. And right now there are no inactive files. And that was that yellow bar that we saw in gross view as well. Okay, that was the data that has not been reused. Now also on this then, so we've got total buffers and how they're breaking out. The other thing that we got here, it doesn't really mark it here, but this is our total amount of memory on the system. 35 gig in this particular system. And 1 gig is for my minimum that I can push down my data, and then the 62 meg is what we're going to try to keep free. These are basically saying on my total memory system, if I have to push the kernel down, how far do I push it down? Okay. And over here then we've got a few more metrics that say how big is it presently, how much do I have free presently, and there's a few other things in here that we're going to take a look at a little bit later. This tick, for example, is something very useful. Now the last row here is just basically giving us the number of times I called getBlock to get a buffer. Did I find it? Have I released buffers? Have I written to a buffer? And there's something called a sticky buffer. And then the activations for inactive, I've got deactivating and reactivating. How much data am I constantly moving from the inactive buffer back to the clean buffer? Okay. And frankly, I often have to refer to the man page to refresh my mind on these things. But think of these three related to each other, giving the physical memory and how it breaks out, and these four are related to each other. Okay? And then total, I've got my total maximum RIL and total max system memory. Now, this tool is extremely useful. Basically, max R is what I'm going to try to keep available to what I'm going to be able to use before I hit a deadlock situation, before I actually kill things. Now they've got some additional slides in here where they're going through some of these other options. But I think I'm going to jump off to a real system and take a look at it. On the next page, 716, it does talk about the min that I can push things down to. There's min file pages and min free pages. Now nbuff says how big can it grow. The more I have nbuff bigger, the more the cache can grow, 64 KB by default. But when I get pressure, I'm going to push it down, and min file page is going to say the minimum number of data pages I want in my cache before I give up pushing the kernel down. Shake-D was the process that was doing this. So Shake-D is going to push the kernel down until it hits one of these two thresholds. It's going to say, for example, if I set it to 500,000, I'm going to push the kernel down until I've got 500,000 pages left in my data cache. And that was this particular metric here. I've got 13,000 in that example. And min free page, it says how much am I going to keep free? So as I push the kernel down, I'm going to push the kernel down until I hit one of these two. That I've pushed the cache down as far as I can, or I've reached a free boundary to keep the two apart. Now it looks to me in my last class like min free pages was not working. Because I basically, even though I had a high min free pages, I was still getting all of my memory being consumed and nothing was being put on the free list. Okay. So nbuff says how big I can grow, and then these say when I do have pressure, how far do I push it back down? What kind of space am I going to try to keep it into? And customers may complain the kernel's growing too big. This is saying if I drop these down, if there's memory pressure, I can push it further down. But what's that going to cause? More I/O problems. Okay. Because now there's less buffers to use, and now you got to compete for those buffers. So this is just trying to give what I've just went through here. We've got the virtual node number of the file. Not of too much use to us unless we can chase it back. Remember, you can have multiple processes reading an individual file. So getting from the file to the process is not always the easy thing to do, unless you can recognize the name of the file and correlate it to the application. With crash, you should be able to track it back, but I don't deal with that in this class. Then you got the name of the file. It's got to be less than 31 bytes. The device, the type of file system, the number of buffers currently holding data, or if it's a system type of thing, it's metadata. Then the size of dirty data, and the high and low are in hex. Or I guess it's decimal for buffers, but for metadata, it's expressed in 5 12-byte blocks. Now there was something else that I wanted to point out. See where we are on our system. So in this particular situation, I got no user load. This is looking at memory, the gross view RMMC display. My kernel is pretty small. I got quite a bit of control data here, some clean data, and very little inactive data. This was the inactive data. So buff view tells me what's in those 3 colors. Okay, buff view is going to give me the names of the files that are sitting in those 3 colors. Let me just keep that up there. And unfortunately also, buff view uses buffers to look at the buffers. So what does that mean? If I've got pressure on buffers and I want to look at them, I'm going to hit the same bottleneck that everyone else is. There are cases where buff view may take 20 minutes to run. I'm going to do a buff view and take a look at what's in there. Majority of the information in there is system data. So I've got 3,000, 2, 2, 2, 2. Majority of my buffers, I got 125,000 buffers, and 4,000 of them are data, but I still got 100,000 buffers empty. Okay? And inactive data over there doesn't show any buffers that are actually inactive. But I've got a few things on the system. I've got somebody did voodoo.tar.zip, and then it looks like aliases for send mail or something like that running. And again, I could dump out the full list. Okay, but I got plenty of buffers on this system right now. Now what I'm going to do is drive up the I/O load. And watch the file system buffer cache hopefully grow. Now remember, count 100 seconds right now. Because I started writing data into here, it's dirty right now. 10 seconds later, it should start going to the clean, and the clean should start growing. And then 100 seconds later, the yellow should start growing as I start absorbing the I/O that I'm pushing out here. Okay. I was hoping to see it grow a little bit more. At the same time now, looking at my buff view, buff view is just showing me the same files that were there before. What? Buff view's recursive, yeah. And it's starting to show some of the effects. I've got this temp file that just started getting in there. Oh, I know what's going on here. I don't have the load high enough, I'll bet. Let's see what I got here. So I'm running one of these code 3s right now. Notice the dirty is starting to go down. It just got absorbed by clean. Actually, code 3 just finished. So I'm going to, and there's another code 3 that just fired off again. What I've got is scaling up. So now I'm starting to absorb the I/O of code 3s again, but I'm going to fix something here. Instead of running one of them, I'm going to run 50 of them. Now let's see what happens. Okay, I've got a few more copies, and notice now that it's absorbing the impact of more copies of this code 3, sucking up everything. But at some point, what I'm hoping to see is the yellows start picking up some of the data that is no longer being referenced that's sitting in clean cache. So we've got to wait a few minutes, and hopefully the yellow should start growing. So right now, my cache has grown to as much memory as I have on the system. Almost. And if I now fire off some memory work, it should push it back down, right? Okay. And let's see if we can do that. Top is showing that I've got multiple code 3s running on the system right now. Majority of them are sleeping. If I do a ps-el and grep for code 3, let's see what they're sleeping on. Buff. Remember the lock name? Buff. One's sitting here on indirect, it's probably doing a seek or something like that. But the majority of these processes are now in an I/O wait state. They're sitting there waiting for the file system to catch up. Actually waiting for a file system buffer cache to provide them with buffers. And if I do, let me just see what we got here. Of course, the response is slowed down because all my buffers are being pressured now. Everything I do is going to require buffers. Even a CD requires opening ITSC password and figuring out where your home directory is. Where'd my, I guess we kind of missed it here, but notice my yellow is starting to grow. It's been about 100 seconds since I started pushing data into cache. So it went from dirty to clean, and then clean to free C. And I have a busy system right now. When you overdrive, there we go. When you overdrive CPUs, it does not affect the interactive performance as bad. I'm going to do a buff view here. And again, it's using file system buffer cache, which is most of memory right now, to do its work. Now this is to my advantage on news server, mail servers, things like that, especially if I increase NC size so that a majority of my cache can be the control data. But notice when the pressure happened, I pushed my control data down into its space as well. It's smaller than it was when I started on an idle machine a few minutes ago. And yesterday we had buff view run for minutes before we got a report, so we'll have to see what happens here. The other problem here is that when you're monitoring a live system with performance tools, tools may not be able to get the metrics until the performance event is done, and then you're looking at the problem after the fact. So by the time buff view actually grabs a buffer to be able to get through this, the state of the buffers are going to be in a different state. I think at the same time I'm going to break off from that. I'm going to do a code 4 here. And now start pushing my kernel down. and see what happens. Okay. So nbuff said how big I could grow, and I'd set it really big. Looks like I got malloc errors, memory not available, so some of my code 4s died. But I still released a majority of my free C, and I'm still pushing my kernel down. Okay, and there are systune parameters that control this. Now, I didn't expect it to go that low, actually. In fact, I don't see a reason why it went that low with this amount of free memory. It should not have pushed, it kept pushing it, it should have stopped. Unless I've got a free C. Let's see what free C is. So my buff view finally came back, and by that time, all my buffers had been emptied. Okay. But now I've got 16,000 that are inactive because I haven't been using the data in near future. That should have been the yellow. Anyways, that's showing a little bit of buff view. I'm going to go on at this point and see what we've got here. It's an extremely useful tool, though, to tell you what's pressuring your buffers. You don't want to run out of buffers. And in one scenario, oh, I know what I should have done here. The other thing with buff view, if you specify by flag, you can look at different types of flags. A question mark will get you the whole report, help. We can look at dirty buffers, we can look at busy buffers, we can look at buffers that are swapped, but I've never seen that one work. We can look at buffers being deallocated, NFS buffers, inactive buffers. That was the one that hung on us yesterday. We can look at inodes, directories, maps, allocation group information, quota information. So there's a whole bunch of flags that we can specify. Now I'm going to do an F and only look at busy. And when I go to busy, there are no busy buffers on the system right now. See if we can get something busy here. There we are. So my node's got busy there. Let me get something going that will actually keep it going for a while. Okay, now we're starting to get some buffers here. I'll just go with this one right now. We've got the vnode number, we've got the name. This is the buffer, the file that the application's actually using. We've got these temps, these TSTs. Device, file system type. This time it's not the number of buffers, it's the buffer number. It's the actual buffer header number. So we're looking at one buffer. We're looking at just one buffer for each line entry. Whereas before, it was all the buffers consolidated for one file and the total number of buffers. Then we've got the size of the buffer offset in the file, but now we've got age, and this age is relative to the tick. I don't like that. I'd rather see it derived. But you compare that age to this age to tell you how old is the data. So this is the present clock tick, and this is the last time the file was referenced or the header was used. Okay, so older buffers are going to have timestamps real old compared to that one up there. Okay, and I've been out on Cray sites where stuff has been sitting out there in buffers for days, not seconds or minutes type of stuff. Okay, and then lastly, we've got the flags, and everyone shows that these are busy data buffers. We saw inodes, we saw directories, things like that. So when I was on a news server, I could actually watch this busy thing and watch the history file come in, and then watch all the inodes come in, and actually watch the system completely thrash cache, where everything was being replaced with either this huge history file or all the inodes for all the news articles. And I was just watching the busy flag and saying, well, what's busy? And I see it flop between one and the other. And at the same time, SAR was showing me negative cache hit rates because my physical were higher than my logical. Okay. Had some asynchronous I/O there. There was some ASs over there, that sort of thing. So buff view has a lot of advantages to it. So going back to the workbook, I really want to stress buff view. The system handbook, for example, one of the things that needs to get added to it is the buff view information. it can save me a week. I used to spend a week looking at systems out at NASA Goddard and stuff like that to identify what was happening with the cache behaviors. This thing could save you a week's worth of time. So anyways, every time a user requests a file, we do a read or write. Remember, we have a user buffer. We talked about that yesterday. Printf, things like that, have a buffer that's default size. Setbuff can change the size of that buffer, or in Fortran, the assign command can change the size of that buffer. Nastran, for example, we can specify in the command line of Nastran to increase the size of that buffer so that we don't have to do as much I/O, reduce our I/O load. So there's a lot of ways of controlling that. It is then copied to the system buffer cache by a routine called bcopy. And then the kernel has to worry about moving it off to disk and handling the blocked devices. And again, cache buffers are written out to disk after they age. And we saw the aging, and we saw the red go down and the kind of magenta go up. And then after a while, if it's not reused, then it becomes inactive. Okay. And the sync system call is what forces all the dirty buffers out to disk anyways. And we'll talk a little bit about trickle sync a little bit later. Now, advantages and disadvantages. Advantages of buffer cache is that if I reuse the data and it's lots of little I/O, I have the advantage of being able to get back to the data quicker without having to do random I/O out on my disk drives to do the physical positioning and seeking. So system call requests can access data directly residing in these buffer caches much faster than reading from disk for lots of little I/O, VI, things like that. It's perfect for that. And also the advantage is that cache will buffer ill-formed requests. It will sectorize it, which makes the I/O programming much simpler. You just say, write this, and then the kernel worries about the format and the size of that thing and blocking it for you. Disadvantages is that there's a significant amount of overhead to manage these buffers. The more buffers you have, the more you have to manage them. And there's additional data movement as well. If I'm not reusing the data, why move it around from memory to memory? Let's just get it off to disk if I'm not going to reuse the data. You know, why pressure the cache resource? And then the user data is vulnerable in cache until flushed to the device. So you still at the end have to sync to be able to get that stuff off to disk. And keep in mind, in Unicos, df syncs every time you run the df command. And NQE runs df every 15 seconds. So you've got a sync in Unicos occurring every 15 seconds whether you want it or not. And some of these are also set up by init tab or changes to the init source itself in terms of how often do I fire off sync on the system side. So it well forms your request for you. The other disadvantage it doesn't list there is that the more people asking it to do work, the more work it has to do, and the less likelihood you're going to get your work done in a timely fashion. And it's subject to public cache pollution. All it takes is one person like me to do what I just did and pollute everything that was in cache. There's nothing to prevent one user from abusing the resource. Okay. Now, with file system buffer cache, we have the concept of delayed write data. When we do a write, it goes into file system buffer cache. And if I reuse the data, I don't have to go to disk to get to the data anymore. It's sitting in memory. So the user data is staged in cache before the physical write actually occurs. And then the kernel, when it put into cache, put sectorizing structures into it. It broke it up into pieces. Now the user can go back to their processing right away. Okay? And then the write doesn't even have to have gone to disk yet. I could actually terminate and not get charged for the writes because I don't do it. The kernel does it for me. I don't even see the block transfers to disk because I'm dead. I'm a zombie. So that's what we referred to as delayed write I/O, where I'm asking the kernel to do my sectorizing for my data. Again, dirty buffers go clean when they're synchronized with the disk storage when there's a flush. And that flush is happening by a command called bdflush, which is showing here. bdflush will periodically flush your buffers. And the behavior of bdflush is changing from release to release as well. There was originally a parameter that said, how often do I wake up flushing? Then they changed it to how many buffers do I look at, basically. And now there's a new parameter called bdflush interval to say how often do I want to flush. On Craze, we do it every 2 minutes. Here, it's every 10 seconds. Again, it's more of a real-time interactive environment. I was going to go to Q2, a few more minutes and take a break. So with buffer delayed write I/O, the request is available to the users, which force the writing of all buffers in the cache that are referred as dirty. The sync is what writes them actually out to the disk drive. Unnecessary overhead would be placed on the system if these requests are issued too often, such as DF. And the more buffers I have and the more of them that are dirty, the more of a problem I have. Imagine a 64 gigabyte system. That was a 16 gig that we had there. But a 64 gigabyte system where I stuff all of that with dirty data, and then I have to push it out to a disk drive that may be 5 megabytes per second. It may take a long time to do that. We don't want to start our next flush until the previous flush is done. Yeah?
Is one sync command sufficient to clean all the dirty buffers out?
Yeah, but that sync may take a long time if I've got 64 gig of dirty buffers. But yes, it does flush everything. They also have flush on panic, like Unicos does. Okay. But yeah, a sync will flush everything, and that's why DF put in the sync, so it could accurately reflect the size of the files, because we were using that information for everything from comparing to disk quotas to data migration. And they had different numbers than DF was reporting. Okay. So a sync will cause everything to flush out. And we don't want to do it too often. Now there's a sync command and then there's a sync system call. Okay. And then the kernel is going to try to accomplish that flush as quick as possible. Now they've been changing this behavior of BD flush, so you have the ability of controlling with systune how often do I wake this up. They've been changing this quite a bit in 6.5, 6.5.1, and 6.5.2. So expect problems. Okay. So the system thread BD flush is what wakes up periodically. The default is once per second. I'm going to go back to do here for a second. Under systune, we now have what's called BD flush interval, and this one's set to 100. To find out what these things are, var sysgen mtune. I'm going to graph for BD flush. BD flush interval is in the kernel interval. It's in 10 millisecond ticks. Okay, so I can control BD flush down to 10 millisecond clicks now, whereas before it was a 1 second granularity. Okay, so 1,000. Weren't we at 1,000? No, 100. That's going to be 1 second, right? So it's still defaulting to 1 second, but they've given us more granularity again in the real-time market, probably. But we slow it down to 2 minutes in our typical compute centers. And it's Q2. Let's take a break. Because some of the stuff we've been through already. There was the question about the sync, whether it's successful or not. There are two options. With sync, I am put to sleep until the sync is done. But with fsync, I will return immediate control. And there's no guarantee that the sync was actually completed if there were an interruption or something like that. So there are two options. But in general, everyone's doing sync, not fsync. And again, if you remember what DF did from like Unicos 7.0 to 8.0, DF got a lot slower when they added in that sync. I reported it with an SPR and they said, well, we got to do that. That's the penalty of having accurate DFs. So anyways, BD flush is controllable and configurable. And it does change in 652M. What's in the workbook on 722 talks about BD flush R. BD flush R you got to be careful about. BD flush R used to be the number of seconds to run BD flush. Then they changed it somewhere in 6.2, and it basically became nbuff. Nbuff divided by BD flush R. It talks about this in 722. Nbuff divided by BD flush R is the number of buffers I'm going to look at each second. Now those that are familiar with trickle sync, this is the closest thing they've got to a trickle sync. Rather than look at every buffer at the system, I'm going to trickle away at it. Okay, so if I've got if nbuff is real big and BD flush R is real small, I'm not trickling. As I make BD flush bigger, I'm looking at less of the total end buffs and therefore getting more of a trickle type of behavior. Not trying to flush the entire cache all at once. I'm going to evaluate only a portion of it. Okay. And those that have used LD cache, that BD flush R would be similar to a trickle sync by number type of concept to try to keep the number of dirty buffers in a certain range. Also with BD flush, when I do flush, I'm going to try to group a whole bunch of buffers together in what's called DW cluster. So whenever I've got these dirty buffers and it's flush time, I try to chunk them together. And DW cluster should be one of those friendly geometry numbers. If I'm pushing to a stripe file system, I'd like it to match the stripe width of my file system. So I'm going to cluster these things together. Now DW cluster is listed here. That's for dirty pages to physical disk. But there's a new parameter called CW cluster, which is for NFS data. And you'd want those to be different geometries because NFS data is being broken up by the NFS traffic into 32 KB chunks, for example. So DW cluster is basically the number of pages that I'm going to group together. If I can't get a full cluster, I'll still do the flush. It's just my best attempt at flushing. Then auto up, as I mentioned before, auto up is how old the data has to be before BD flush will select it and flush it out to disk. And the default was 10 seconds. Whereas on Craze, it's typically like 2 minutes when we do our flushes. We don't do our flushes as often. And again, the real danger here is if I take a file system interruption, the contents of the cache may not make it to disk. That's the reliability danger. Let's see. Yeah, if it's metadata, DW cluster has no effect. It doesn't work on that, just on data buffers, not file system control buffers. Okay. And again, as I pointed out, it's not listed here. There is another parameter now called BD flush interval. That's where we left off just before break. You might want to write that one down. That came about in 6.5.2. Now on the next page, 724, VFS sync is the systune parameter to control how often do I flush my metadata out to the file system. So like, for example, on a news server, we may slow down that flushing because we're constantly creating and destroying inodes. And we don't want to have to get tied into what the disk device is doing. In general, 30 seconds is appropriate in most compute servers because we're not opening up tons of files. Okay. It's more in the, with the web server, it's not a big issue either because we're not modifying the inodes. But it's more a property on mail servers and news servers. That's where it's really a big issue. And the other thing to point out here is NC size, though it's not mentioned here, will control the size of my metadata as it resides in cache. Making that bigger will allow my cache to be dominated by metadata, file system control data. Going on, we then have buffered synchronous I/O. This is the default for everyone. Everyone basically does it. They open a file and write into the buffer. When the buffer's full, we write it off to file system buffer cache. And the physical blocks may or may not be read prior to a write. I've noticed quite a bit that the logicals over physicals are a lot better in Irix than Unicos. In Unicos, you usually see some physical behind it, whereas in Irix you don't because this cache is so good at absorbing it. The problem is when you oversubscribe it, then you're in trouble. Synchronous I/O has a negative effect on the performance of a user job, but that's really a property of what can you do while you're waiting for the I/O. If you can't do anything, why do it asynchronously? But in, for example, Netscape or something like that, we initiate an I/O request. We want to come back with control. We can do that. That makes sense in that situation. Web browsers are one area that uses everything. Asynchronous I/O, local caching. Netscape has its own cache concepts, all those sorts of things. Then we've got buffered I/O with library level routines, such that when I do an fwrite, for example, I write into a user buffer, and then when that buffer gets flushed, it's going to go into a library buffer. The default was 8 disk sectors or 4 KB as the default library buffer size. And setBuff would allow me to increase the size of this buffer. And by the way, unfortunately, in Irix, a lot of the tools like copy, tar, XFS dump are still doing standard Unix buffer sizes. They're not optimized to larger buffers. And for example, remote copy and FTP, those are being used at one site as 3/4 of the I/O on the system, but they're doing lots of little I/O on large files. And one of my recommendations to the site was that they use bulk data service instead of remote copy to stage their data off the system. And they had a /archive concept that they were moving all their data off to. So the library routines are going to manage that library buffer, both the library buffer and the user buffer in the data segment of the program. And again, if you're in Fortran, the assign command can control the size of that buffer. Okay. So that's file write, fwrite. And in this one, they're doing a fread, reading in data from cache. Nothing new there, really. So with buffered I/O, just go through the list. Advantages: the library buffer collects the data from small requests in order to make one large system call. And ironically, by the way, on Unicos, our library buffer sizes still default to DD29s. And unfortunately, with the VxWorks operating system on the newer iOSs, it's doing it at 38 blocks, not 48 blocks like the defaults have been. It's doing it at 32 blocks. So anybody that hasn't dropped their default buffer sizes in Unicos and are running the new VxWorks are wasting bandwidth. And benchmarking people will tell you about this. But the default is because of the older iOSs that are still out there. But it's the same sort of story. We want that library buffer to be a whole-friendly number of the geometry of the file system we're going to send our I/O to. So it's typically page sizes, multiple sector sizes, track sizes, cache line geometry sizes, all these sorts of alignment questions. If you go to that disk aligned man page, it'll talk about all of these different issues. It does a pretty good job of it. So if I were to write a terabyte of data 1 byte at a time, I would not want one small buffer, 1 byte, and one system call to do it. I'd like to buffer it into a file, make it big enough to make it worthwhile to send off at least a block or at least a track, something like that. And there's applications like Disco and stuff that have always been doing it in what's called track I/O. These library buffers are set up to track sizes or even cylinder sizes. If the library buffer is an integral number of data buffers, then the library buffer collects those ill-formed requests and may block them. You have different controls of this library buffer. And I can put in a library interface that says block it when it goes into the buffer and put control words into it. Then when I send it off to disk, it's already been sectorized. And I don't have to ask the kernel to do it. So a well-formed I/O request is one that maps directly into the I/O device geometry. It fits into the geometry properly. Disadvantages to this cache: extra data movement, there's extra CPU overhead to manage the library buffer, and the I/O request cannot be performed asynchronously because the CPU is moving the data from user to library. It's shuffling it around in here. Now in the future, as I mentioned before, I'd like to see asynchronous double buffering, so we got 2 of these library buffers and we're flipping between them. But I don't think that's being supported yet within Irix. I haven't seen it yet. But that's standard in Unicos. Asynchronous double buffering is almost automatic these days. Then direct I/O bypasses file system buffer cache. Basically, when you open the file, there's an O_direct going on in there. Okay. So direct I/O bypasses the file system interface, the file system buffer cache interface, I should say, and does I/O directly from user space to the device. There's no copy from user space to a kernel memory address and then a copy of the kernel memory address off to disk. It goes straight from user to disk. So the B copy is not involved in this. And that's one of the reasons you can get better performance, especially if you're not reusing the data within 5 minutes, for example. That's always been my threshold. There are restrictions when you do direct I/O. It has to be aligned. So when they create this user buffer, it has to be properly aligned. It has to be well formed. So there's a user data alignment. It must be aligned on a secondary hardware cache line boundary. So it's got to be on a 128 byte boundary. The minimum I/O size, all file must be done in multiples of 4 KB. The file offset pointer is positioned at multiples of this unit. And then there's a maximum I/O size. When you're doing direct I/O, the maximum you can do is controlled by max DMA size. So if I start striping 128 disks wide, and I do an I/O request that's that big, max DMA size has to be set up such that it will allow me to do that large of a transfer. Otherwise, max DMA size will break it up into pieces. And on Unicos, the max DMA size is 32 4K byte blocks. I should say that VxWorks puts that limit on the newer iOSs that we have. So they've got a 4 megabyte one. What's ours? 4K byte times 32. 128 megabyte is the size that we can do. And they're showing this file where they've got an offset 0 for the beginning of the file, then as they're transferring the file, they've got a current offset, but all these offsets have to be aligned on proper boundaries. Now when you use Fortran in the assign command, the Fortran I/O libraries will ensure alignment for you. Okay, but if you're writing your own Fortran program, doing your own I/O, the application tuning class has examples of how to make sure that you've got everything aligned on these hardware boundaries. So it's got to be a cache line alignment as well as a sector line alignment, and a lot of sites it's also a track alignment where they want to make sure that it's aligned to the geometry of the tracks. So some of the disadvantages. First of all, advantage, there's less system overhead because we don't have to manage the buffers. There's no H chain to manage, there's no B tree to manage. We simply get the data out of memory and do the I/O. There's no intermediate buffer involved. However, from a user point of view, an individual job could execute longer than buffered because the job that did delayed write let the kernel do the buffering. Now I've got to do the buffering. So that may cause my service time in my job to run slower. But at the same time, I'm not dependent upon somebody else abusing cache. So I'm not going to get hit by somebody that's writing 10 megabyte of data into cache and consuming all of it. When the kernel returns control back to the user after direct I/O request, the user has assurance the data has reached the target device. It's ensured. Disadvantages, the user can issue only well-formed blocks. They have to be aligned. If it's made on an ill-formed request, the request will fail. In Unicos, we just force it through cache and say, you don't know what you're doing, push it through cache to sectorize it. Here, you will get a failure. In general, a user job making direct requests will consume a greater amount of execution time. With buffered I/O, much of the time is consumed to populate and flush buffers. That was the responsibility of the kernel before, not the user. Now it's in user space. Also, I might point out in 6.5 or with the assign command in the 7.2 compilers, I can put in cache layers instead of buffer layers. So rather than having a public cache pool, the assign command, I can create my own private cache within my user space for reusing data. So I'm still taking a memory footprint, but now it's in my space rather than kernel space. But nobody can pollute my cache on me. And I can set the cache line pages and the number of cache pages as assign options to say how big do I want this cache. And this was based upon Nastran. It was originally written as the EIE I/O layer to do Nastran I/O that's a very predictable sequential I/O type of situation. If you're doing random I/O, caching is not going to be very good for you. And this one's just showing the user process, doing direct I/O, reading it in, writing it into a buffer, and then writing it off to cache where it goes off to disk. And the system call interface is all done through the reads and writes. And again, I like to call these things stopover points for the data. I use the old fire bucket brigade. Each person in the fire bucket is one of these stopovers. And we've got the array. If we follow the data path, we've got either an array or some sort of local variable that's sitting in the program, probably in the data segment. Now it could also, again, have within the data segment, so to speak, the library buffer. So whenever I'm doing my I/O, it's going off into this library buffer. Then I'm making a system call into the kernel. And in the kernel, it could be going into cache. And those, remember, were all 64K bytes. This one was 4K bytes. Okay, by default. And again, I could either be going into cache or I could be bypassing cache. Now, coming out of cache, where are we going? File system buffer cache. We're going off to the XIO board, and it's got a hardware buffer within it that's got a limit. So it's going to be breaking my data up into pieces. In fact, the XIO board has a little LED that flashes on it when that buffer's full, stuff like that. And off the XIO board, then we're going off onto a PCI bus, okay, which is breaking my data up into pieces. Then off the PCI bus, we're going off to, for example, a SCSI channel. So we've got some sort of SCSI board that's staging our data off the PCI bus, and this then got to go off to my disk drive, but what's in my disk drive now is a hardware cache. And then we eventually get off to the disk drive. So I've got where I started, seven different stopover points for my data. So as I'm shuffling all my data around, I want to make sure that everything I do is the maximum. If I'm doing large data, the maximum that I can take advantage of it, so I'm not spending all my time in protocol breaking it up into bytes and sending it across things. Now there is one other stopover point for data in here. MBuffs for network traffic. And those are typically like 1K byte. And off of there then we go off onto our routers. And what's the geometry question for a router? The maximum transmission unit, the MTU. And then you're off to the other workstation, whatever you've got off out here. So this is just trying to bring up the concept of friendly data movement, the fire bucket brigade concept, where we've got all these stopover points for our data. We want to know the size of these things. I start off the class talking about tuning being a system sizing situation. What I'm trying to do is understand the nature of the data movement and then properly size everything to these whole friendly numbers and make sure they're aligned to the geometry of the hardware that I have underneath the system.
So when you size these things, though, do you look at the largest possible cache or the small?
Well, no, that depends upon the nature of the application. If I'm doing lots of little I/O, I want them small. If it's large sequential I/O, I want them large. And everything goes back to understanding the par traces to characterize what the applications are doing.
Yeah, but what I'm saying here is that these caches are not linear in size. You went from 4 to a 64.
Right.
Can you squeeze back down?
Yes. Remember that the 64K byte was the default. And by the way, this is typically a 512K byte cache broken up into 8 segments, which is 64K byte. And then we've got the stripe unit out here. That's 64K byte. Okay. So when I mount the file system, the mount can drop that down. With FX, I can drop that down. And the way I create my file system with the make FS and stuff, XLV make is going to allow me to drop the stripe unit sizes down if I'm doing little I/O. And if I'm doing large I/O, the highest I can get these things to is 64K bytes. So if I want to do huge I/O, I want to bypass that and then make sure that this hardware cache, for example, goes larger. In the video market, they'll go to one segment and make it write buffering and use that to sectorize my data and not share it between reads and writes or things like that. And then again, just get the stripe width. You may have stripe units at 64K byte and then get a stripe width that matches everything. So your data stream is going to get broken up into pieces, but depends upon what's going on up here, whether you go down or up. So it's a latency versus bandwidth. In database markets, you're typically small. In video and satellite data reading and stuff, you're typically streaming large sequential data. Nastran is large sequential. Gaussian is small random. So the first job of the tuner is to understand the workload to properly set these things up.
That's really predicated, though, on purchasing the right equipment.
Yes, which is a common problem. Like I said before, there was a Canadian black hole site that got a bandwidth Ciprico drive, and the application was doing 4K byte transfers, and it performed terribly. And when they pulled it apart and narrowed the stripe width and stuff, Randy Kreiser was the one that went out there and solved their problem and took a bandwidth device and made it as latency oriented as he could given the things that he had with that particular drive. But his first thought was, oh no, you know, somebody sold the wrong drive based upon capacity, not requirements or understanding the application. And this happens quite a bit. Now in the Cray market, it's not uncommon to have both types of applications running on the system. One that's doing lots of little and another one that's doing large sequential, Gaussian and Nastran running at the same time. That's when you try to segregate them into separate file systems so that the hardware paths are different. So that's what I mean by stopover points, friendly data movement, and sizing these things to the nature of your application. You'd like to fix it at the application first. So with Nastran, I can up the library buffer, the assign command can up it if I'm doing large sequential. So solve the problem here first. Then solve the problem out here because you eventually have to do I/O to disk. And then match paths in between. Now there's a little tool out there called disk prep. And it was supposed to be in 6.5 too. What disk prep will do is go through the list of disk drives on it and reset these for video markets where they set it to write buffering, 1 cage, so it's basically a 512 KB chunk, and they set all these things to the size of a video stream. And they even go through an example of how to configure or figure out what your request size is based upon the video format, pixels per frame and all that sort of information. We not so much on the drive. We take one drive per partition and spread them round robin among XIO boards and among SCSI channels and fan out as much as possible. And one of these sites has got one drive per SCSI. Another one may have 10 deep daisy chain SCSIs. And both have their trade-offs. The more drives deep, the more data there, the more contention to go down that single path to get to it. And Cray, we've always done it by fan-outs. The older iOSs over-fanned everything. Okay, now we're under-fanned, but now we're using third-party vendor cards within S-buses or PCI buses or things like that. And I myself want to get some more background in these particular areas in terms of what the hardware is doing and how it's breaking it up and stuff like that. There's a 512 KB buffer in here and those sorts of things. But how is it being managed? So when your first question is what type of I/O am I doing and is it best, and solve it at the application first. If you can't, like a database transaction thing, then you have to drop the geometries down. And 64 KB was just picked as the middle of the road. And EFS doesn't have this, and EFS is better on your workstation because of the nature of the things you're doing there. But EFS is becoming obsolete. They don't want to support multiple file systems. And systems are getting bigger nowadays, and disk farms are getting bigger. So just think about that in terms of crossover points, because eventually after I've derived all my data, it's then got to get back out to the buffer. So I had 7, 8, 9 through X, whatever routers are along the way, and then your final destination where you want your data. And trace route is what's going to tell you how many routers are potentially in between and give you information about the path in between. I had one class where everyone else was doing fine with VIs and LSs and stuff, but mine was timing out after half an hour because I was looking at megabytes of data. I was looking at a month's worth of SAR and accounting data, and I had a lot of data points, and just one window was timing out trying to plot, 100,000 data points. But everyone else was fine because the MTU was real small. They're only pushing, 4 KB or something like that in an MTU. But if I'm moving a terabyte, it breaks it down into so many pieces. I wait forever for all those pieces. Anybody that's tried to go between Mountain View and Cray type of networks, you've hit router problems in Mountain View, I'm sure. If I'm off in Detroit and try to get to Egan, it's real bad. Their routers are set for switching lots of little pieces, which is good for browsers and stuff, where I'm transaction-based and breaking up into lots of little pieces. But it's terrible for X11 or VIs or things like that. And that's a trade-off they made, latency versus bandwidth. So that's the stopover point concept. Let's see, we've been through some of this stuff. XFS features to enhance I/O, there's delayed allocation. That way we can get a better idea of how big it is, and that way we can avoid fragmentation. But you still have files that have trickle growth to them, and they're the ones that are going to fragment more easily. So we're trying to avoid file system fragmentation. There's read ahead. As my heads are going past the platter, I may as well pull off what I'm getting and buffer it with the likelihood that I'm going to use it next. Because if I'm doing sequential I/O, the read aheads are to my advantage. Okay. If I'm doing random I/O, then I'm wasting the overhead, wasting memory space to buffer that read ahead stuff. Write behind is basically like delayed write. We're going to write the data as we go past the heads. Direct I/O we talked about. Multiple process, single file I/O. All these files can have multiple processes writing into them. NQS is one example. The NQS debug trace has to be synchronized by a process called log daemon. Otherwise, every job could end up writing into the debug trace at the same time, and you'd have alphabet soup. So you have to synchronize and lock these files to single thread things through it. And that's what the log daemon does for NQE. And also efficient file system metadata updates. We're taking some heat in that area. The AOLs and GTEs that are doing mail server storms, and right now they're pounding the systems with spamming storms essentially, and trying to avoid service denial because of a spam storm. Somebody out there with some sort of server that's firing off a couple million of the same messages to every user on AOL. Okay. Now this delayed allocation just talks a little bit about here. We're going to stuff it into cache. The more CPU intensive it is, the more CPU work it has to generate the data, the quicker it's going to fill up that cache, and the quicker I'm going to get an idea of how big it's going to be. So delaying the decision helps allocate things. Also, remember in the allocation process, we've got the trees sorted by free space, and we've got extents that are grouped together. So there are other things that help us prevent this fragmentation. For files that cannot be entirely buffered in memory, delayed allocation allows the file to be allocated in much larger extents than would be possible, but you still have allocation problems. An example of that is video. Okay, video is something that's going to creep growth, right? If you don't have a pre-knowledge size, what they'll do is they'll do a make file or something like that and then hope that it's contiguously allocated. So they're doing their pre-allocation with this make file command. But otherwise, you start off with a small file and you creep growth, and then XFS has no idea how big you're going to get, and it can't make it contiguous. It can't guarantee that. So we do need some pre-allocation clues that will help us as well. So fragmentation avoidance. There are a variety of things that affect fragmentation. Number one, don't run your file systems full. 95 to 99% full file systems are going to be fragmented for sure. That's just the way it works. The bigger your disk, the quicker you can fragment it too. So they try to avoid fragmentation but through delayed allocation, and file systems are typically very large unless you want to save disk space like the Disney site. Disney was 99% full all the time. They said, well, it's a big RAID, but you don't have any breathing room in the file system for dynamic allocation and deallocation. Remember when NASA Johnson was complaining about performance of Nastran on a J90. When out there, it was 90% fragmented, and their entire file system was one disk drive. Okay. So they were running it big, real full, and just fragmenting everything. I have a little script called fragit. All it does is make big files, little files, make a big file, remove the big file, remove the little file, and randomly create and release big and little files, and that will fragment your file system. Just like we talked with that cache fragmentation. The little file gets sent off in the middle, then we create a big file, then a little file, and they all end up little files scattered all over the place. There's no garbage collection. And defraggers are trying to put files into contiguous pieces. But fragmentation collectors are just trying to shuffle all the small files into the same area on the drives. That way I still got lots of breathing room or headroom there. But in the meantime, you just got to run your file systems less full. My rule of thumb was 80% or less on a file system full condition. And your file system will start slowing down when it fills up because I've got to go through more allocation groups, and I'm going to try to get that contiguous piece, and if I can't, I'm going to spend more time doing the search. So you actually get a choking off of your file system as it starts filling up. It's not an intentional throttle, it's just the amount of work it's taking to try to find and solve that contiguous allocation. So file systems tend to be used to store a small number of large files or a large number of small files. Allocating and deleting large files still leaves large regions. In a file system with lots of small files, fragmentation does not become a big problem because the small files don't need large regions. But mix the two together, now you've got a problem. And that's what Disney's problem is. RAID device out there, everything in one file system, doing all types of different I/O in it, production I/O, scratch I/O, all that sort of stuff. Now at the same time, they've got some origins there that are running RenderMan that are doing the rendering, doing the CGI, the computer graphics imaging. That's all CPU intensive. That's all geometry. So their CPU farm is fine. It's their file serving farm with all their O2s cross-mounted with all their home directories on this RAID device that has a very diverse request size characteristic going on with it. And they really need to split out their NFS server environment and segregate their I/O traffic. But then you've got the administrative issue, the cost of additional disks, all those sorts of problems. Okay. And like I said, most of these sites, the number one thing they need to do is not spend $7,000 to have me tell them to do it, but to actually just go out and buy more disks. They do it, yeah. It's in the budget and stuff. At Disney, not right now. It's being considered, but there's money needed. They don't have enough with what they've got. And what they really needed to do was get off of RAID 5 and go to like RAID 01, segregate their file system, and you're talking about several more drives, and it's not in their budget. That was the first thing they said was, we don't want to spend money on the drives. Anyway, DreamWorks and a lot of these other sites have the same sort of problem because of the NFS environment and trying to make everything homogeneous and easy to administrate, because all the files are off on one NFS server. But then you've got the moped between the semi-truck problem. Somebody's going to get squished. Read ahead is just saying that as I pull data off the disks, I can read the next buffers and decide whether I'm going to use them or not. And it's useful for sequential, not so useful for random. Nastran, for example, benefits from read-aheads. Gaussian does not. And then right behind is a mechanism by which the user data is physically written to the devices after the write request was returned to the user process, which is like a delayed write. And it's used with the delayed allocation mechanism so that we get a better idea of how big it is. And then XFS uses the BD flush and aggressive write clustering, that CW cluster and DW cluster. DW cluster was for direct disks, and CW cluster was for NFS traffic. Then I'm going to group them together into a piece and then push them off to that particular file system. Now, direct I/O is going to be faster. Applications want full bandwidth of the underlying drive. They're going to bypass file system buffer cache. If it's a reuse situation, there are better things for user caching and things like that. And that's what a lot of applications are doing nowadays. Domain name service type software is caching DNS information. Netscape caches it. Unfortunately, where does my Netscape cache my data? In an NFS server. Okay, so it's kind of silly in my configuration. I've got a web server sitting out here with the data served off of NFS. And then I've got Netscape sitting there caching, and it's going right back to the same disk drive that it originally came from as I use a web browser to get to my own data. Because .netscape is where your cache is for Netscape. And I've tried moving it, but then it ends up getting scrubbed or something because I put it in temp or var temp. At least then it'd be on my local disk rather than going across the network for it. Buffer cache can be a bottleneck for very large files because they can take all the buffers on the system. Now they got to wait for buffers rather than just getting the data off the system. And again, Cray environments have been traditionally direct I/O, what we called raw I/O. This one's just showing that we can have multiple processes writing into the same file, working on the same buffer cache. Remember with buff view, I said this is the vnode number, but multiple processes could be doing I/O into that file. Now, XFS says efficient file system metadata updates. There's what's called the transaction log. That's the XFS log, journaling for recovery of the file system. We also have data structures using what are called B trees rather than the traditional Unicode where we had bitmaps. Now, it worked on a Cray because we had bitmap hardware. We could do bit operations and go through bitmaps and look at them, you know, pop counts and things like that. Those aren't available within these chips. So B trees are much more sensible for them. And remember with FS tab, when you mount the file system, you can control the size of this transaction log. In other words, the size of the writes. Anyway. Now, sequential versus random I/O is again the nature of the data that's in my array. In physics and stuff like that, you have sparsely populated arrays where the data is just in pieces. Chemistry codes are typically random I/O. Whereas you get into codes that are like Nastran, where it's just a sequential stream of data. Or the image processing for satellite data that's coming down, and I run it through an FFT. That's a streaming situation. So sequential is used in some cases, random in other. Majority of Cray applications fall into both areas depending upon the type of application. The key difference now with random I/O is we've got this LSEQ system call that can position me into the middle of the file. And random I/O can cause lots of problems in your cache as I'm doing random reads and writes and got all these little buffers that I'm constantly refreshing and changing and fragmenting file system buffer cache. Let's see. Yeah, LSEQ being the call to do random. And then synchronous versus asynchronous. With synchronous, that's the default. I go to sleep on that lock until it's done. And the two locks we talked about were the buff lock and the BIO lock. Buff lock was for cache, BIO was for physical, going to disk. Okay, there are other locks, but they're really not timed. There's an inode lock, there's a directory lock, there's an XFS log lock, those sorts of things. And again, most applications in the Cray world did synchronous I/O. With asynchronous I/O, you have to have something to do. In the network area is where you're commonly finding multi-threaded applications that are doing asynchronous I/O to handle all the different tasks that they have responsibility for. Anyway, there's a comment there about O_sync. You can look at that on your own. Now with asynchronous I/O, the difference is you're making AIO system calls. Instead of read or write, you're going to do an AIO read, AIO write type of thing. And in this scenario, I go off and return control as soon as that AIO write is done. I continue with the next line of code. And I'm going to wait for a signal to come back to notify me that my I/O is done. Does it list the signal? No. We'll see the signal in a later chapter. And then there's also something called list I/O. And list I/O basically says I've got a whole list of I/O requests. I make one system call and fire off this list of things for it to do I/O in. And that's used quite a bit in the traditional Cray market. There's a lot of applications, petroleum area and stuff like that, where they do list I/O. And again, with list I/O, you're notified through signals of the I/O being done. Now it's possible to have conflicts between two processes writing into the same file, or one writing while the other one's reading. So by default there is no locking, assuming that we're getting into file locking here. You used to have that real problem. If I redirect standard out into standard error into standard out, are two different buffers going into one file. And I had one site that I was working a bug, and basically we had I/O diagnostics in the middle of the word water, because of the time that the two buffers were actually flushed out to disk. And it was past column 80, we couldn't see it. It was an IBM type MVS environment. We couldn't even see the error message because it was where it was, buried in the stream of data. So you get into file locking. File locks and record locks, so that you can lock the entire file or lock pieces of the records. There's read locks and write locks, and it was basically standard Unix introduced at System 5 Release 3, and we had locking within Unicode as well. do the same sorts of things to prevent multiple processes from manipulating a single file. And FCNTL is the file control interface to do this locking. That's the system call to do it. So in this case, they're locking just a few bytes, saying that no other process can write or read depending upon the type of lock that I've set on that piece of the file. But by default, there's no locking. We also have advisory locks. So we can lock things with FCNTL. They're typically advisory only. They're not enforced. In other words, for locks to be effective, all processes access the file must faithfully use the locking mechanism. Okay, so it's a synchronization event, and if you're not checking that synchronization, the file's not locked to you. It's really just an advisory situation. Yeah, it's just saying here again, they must faithfully set the appropriate lock before performing their operations. And it's up to the programmer to enforce the locks. And the locks are within the inode structure. And for example, in this case, we have a lock, capital L indicates a mandatory file record locking being enabled. And with mandatory file locks, it's on the whole file. Suppose that a mandatory lock set on a particular file, A tries to open it for reading and writing and uses file control to check it. Another process having permission may open the file as read and issue a read on it. And there's no mechanism to enforce the locking by default. So this is enabling mandatory locks to actually do that. Anyway. And then the kernel has to manage the stuff off the vnode. They have these file lock structures that maintains a list of locks for each file. It's called an flock structure. So that's where the locking information is kept. We also have memory map files. I'm just going to go on here. Memory map files are things where I've actually pinned the mapped the thing down. Device drivers do this. Graphics devices do this. So we open the file and then we do an mmap system call or an mmap library call that's going to result in it locking. And then the reference to the file actually points to where it resides in memory. And then you can control that with write only or read write. And physical I/O is only done when necessary. Now it's saying it's PD flush. I thought it was BD. Yeah, PD flush, right. I'm sorry. PD flush is the one that does this. It's like BD flush. I was mixing up my B's and P's. Okay. So PD flush's job is to write dirty pages that have been mapped with mmap to the disk. Now looking at file system buffer cache, SAR-B is the metric. Over on the right, we have physical I/O. In this case, P-read and P-writes. I do see a couple of events where I have physical I/O operation occurring. But in general, those are typically file system backups or something like that. All of my I/O is typically going through cache. So in my cache, I've got these metrics. B reads are the number of blocks that are going from cache to disk. So going back to this display, this is my B read right here, or B write. This is my P read and P write. And this is my L read and L write. And over here there's a SAR-C that said number of bytes read and written. So every time I make a system call, I've got to read, and one of the arguments in there, we've got the file descriptor like 4, we've got the offset, and then we've got the bytes. So it's basically just taking that byte count and adding it up to give me the SAR-C. So I may do 1 byte, but then it takes a 64 kbyte cache, and I may actually end up moving a whole block of data on the other side of this chain. So these are in blocks, 512 byte blocks. These are just the calls. These are not the blocks, these are the number of calls. And then over here with SAR-C, we can see the actual number of bytes that those calls are asking for. So B read is saying in this case, I had 13,900 logical read system calls occurring on the system, and I had to go to disk for 1,654 blocks to satisfy those logical requests. And that gave me what's called a cache hit rate of 88%. Now the cache hit rate is derived, let me put it down here. Basically it's L read minus B read over L read, and then times 100 to get it into percent. So we're basically describing what percentage of my references did I satisfy out of cache. The better my cache hit rate, the better my reuse and the better my data is being satisfied out of that cache resource. If that's going down, if B reads get bigger than L reads, I actually go negative. And in that case, I may have more traffic going on here than I have going on here. And that means that my cache has flipped. Possibly I've got this program referencing two files through cache, both of which are as big as cache. So I read a file, doesn't fit in cache, so I have to free up whatever's in cache, push it out, read the other one in, and then suddenly I go back to the other file and I got to flip back and forth again. And this was the example of that news server where the history file was as big as cache and metadata was also as big as cache. So the metadata and the history file were thrashing back and forth between disk and cache. And my hit rates were actually negative in that scenario. And BuffView showed it. BuffView showed the names of the files that were actually causing the thrashing. And from the name of the file, you hope to get back to the application and make some sense of that. So in this example, my typical read cache hit rates are in the 80s or 90s. I did have one case here that was 58, but I wasn't doing much. I was only doing 1,000 calls. I was doing 13,000 calls here, and I got an 88% satisfaction out of them. Whereas this one, I only did 1,000, but only got half of them. So this is more a property of the abuse of the system, not the reuse of the system. What I try to tell people here is I can increase the size of my cache, more buffers. No effect in the hit rate, because the bigger the cache, the more I can abuse it. The hit rate's not describing the fact that I asked for more here. Okay. Whereas there's another metric that's called the ratio, which is logical over physical. L read over B read. And this is a better measure of the way the cache is performing. If my L read is big and my B read is small, that tells me that I'm getting reuse of my data. So the hit rate may not change. I've got a bigger cache. It just allows me to abuse it more. But at the same time, I may get a better ratio out of that same situation. So a lot of people try to increase nbuffs when they see bad cache hit rates, when in fact it may not be helping them because of whatever's going on elsewhere in the system. Sizing them or the size of these caches or something like that. Okay. And if I'm writing 1 byte and I've got 64 kbyte happening behind the scene for me, that's wasted overhead. So the read cache hit rate is only one indicator. The two other indicators are the ratio, which you have to derive yourself, or using BuffView to look at the contents of the cache and determine whether the data there is useful or not. B writes and L writes are going the other direction. So logical write, in this case I did 296,000 logical writes. So I was writing more than reading at that time. Okay. And I only had to write them to disk 952 blocks. There were 952 blocks, physical reads or physical writes that went from cache to disk. That gave me a 100% write cache hit rate. I did not have to go to cache or go to disk to do that. So that kind of shows an example where my cache absorbed. I wrote something into cache and it absorbed the whole thing and grew, and I didn't have to squeeze it off to disk because there was plenty of room in my cache to hold it. And hopefully I'm going to reuse the data. Okay. Now what I really wish that we had on this report was also the number of buffers used and the number of buffers allocated. Remember the BuffView statistics? Total number of buffers and then the breakout between metadata, page data, inactive data, that sort of thing. That's what I'd also have. Because this isn't telling me how many buffers I'm actually using. If I configured it for 5,000 buffers, I'd like to know how many I'm actually using because I can get pressure there. It'll eventually show up in here, but the other number is also extremely useful. I've been on a lot of systems with good cache hit rates, but still had cache problems. Now there's another metric in here called write cancels. These are typically related to random I/O. Okay, I wrote something, I read it, and then I wrote it again, and therefore I have to cancel the previous write if it has not flushed to disk yet. Sequential applications typically don't do it, but randoms do. Now that's just a thing that I trigger off of when I see it. It makes me think random I/O. And again, the last two are just indicating physical I/O. See if there's anything else of interest here. Oh, it does give the metric. Yeah, good. It does show how read cache and write cache are derived. Now this is an example here where they brought up gross view, and it looks like I've got high system time. And then we're able to see here, I was trying to demonstrate this before, but I had an application coming along. The high system time is probably due to system calls occurring. And I can look at the system and see that I don't have any memory shortage going on. My cache is here. I've got quite a bit of dirty data, a little bit of clean, and a little bit of free C. And if you look at it in terms of a time lapse, we can see that the workload started here and my cache got dirty. But then the dirty started going into the clean, and the clean started growing. And then right here is where the inactive is starting to grow. So this is probably about 100 seconds that's here and about 10 seconds that's in there. And auto up was what controlled dirty to clean, which was default 10 seconds, and then clean to free C, which was 100 seconds. Okay. And the stuff that's starting to grow here probably existed in cache at this point here and was then getting pressured out. And there was no real user memory pressure here. We had a little bit of user work that started off, but plenty of memory still available on the system. And lastly, looking at the memory map, here's my memory. Here's what's being reserved. And then here's my swap. And I've got virtual swap as well. And there's nothing being reserved or allocated out on swap. It's all this cyan. There's no yellow, magenta, or green showing up there. Okay. So we've been through this display a couple of times. It's the same thing as SAR-R. And then buff view will tell you the contents of that buffer cache area. Here's another example. Again, I guess not a whole lot more here. Seeing an application running, a little bit of system time. Here's our memory map. We see most of this data is clean. And in fact, can't really see it here. The inactive was bigger here, and it's being pushed down for some reason, but I don't see any memory pressure that would have caused it to push down. Maybe the initial event here, but I don't see any particular reason why it should have been pushed down from the data that I have here. And again, there's not much to the swap display in this example. Character devices, just showing a list that when you do an LS on a character device, you're getting a major device number and a minor device number in the LS report. I'm not going to spend a whole lot of time on character devices here. All these are showing just TTYs that we've got there as character devices. Notice they had a C in the first field. Now, character devices are controlled with IOCTL. It's the system call. This allows me to set terminal attributes, do things like rewind tapes, control my networks, process memory errors, and also controlling the console logging features, things like that. So there are a variety of things that are done through IOCTL, including the tension processing unit, the TPU. There's interfaces to control that thing. You've heard of the TPU? Because I know that there are some people here working on it. IOCTL is one of the interfaces to it. We don't really do reads or writes to it as far as I understand. It's all controlled. There's an IOCTL interface into it. And every inode for each device is in /dev, has a C in front of it. And /dev is being replaced by /HW in the Irix world. So they're trying to show a terminal console here. When I log in, there's actually a pseudo terminal driver in there. Older Unixes were based on physical console drivers and had that Getty program, but now we're coming in through telnet connections, and that's where we get into pseudo terminals. And the pseudo terminals will have a Q within their character device name. And here we're looking at a TTY command showing us what terminal I'm on. did a who am I, and then catted into that character device a whole bunch of stuff, and it came right out on the terminal. They also did a word count and counted that it was 218 bytes that were actually transferred in that transfer. So here they're just using and doing I/O directly into dev TTY type of interface. And traditional terminal drivers, nothing of interest to us here. I'm just skipping over a couple pages that don't have a whole lot on them. Pseudo terminals have master-slave devices. We're just showing here that in /dev, we've got the TTYQ0, but in dev PTS is where we actually have the pseudo terminal device pair. We don't really need to worry about this stuff. So when I log into the system, basically SCED has forked off init, and init has created inetd. So inetd is sitting there and it's actually listening on service ports. Suddenly a telnet is run somewhere on the network and I get a notification to inetd. It then forks off telnetd because it was a telnet on the other side. If I was doing FTPs or other types of interfaces, remote login, inetd would see those on different service port numbers and then would fork off a different shepherd to control it. And then telnetd is going to fork off the login command. The login command will prompt you for login password and then set up your user environment and your credentials and stuff like that, and then exec the shell on top of it. And from that point on, the shell is forking and execing any sort of command that you type into standard in. And we've seen about ITSI password already. So, and through a pseudo terminal, when the remote user issues a telnet, the telnet daemon receives the request after a socket connection is made. The telnet daemon opens a master-slave character device pair that's used to emulate the terminal device. And then the telnet daemon forks a child that executes the login command. That's kind of carrying on from where we were before. So we're seeing telnetd opening the master, the slave, doing the fork, closing the slave, and then doing the reads between the master terminal and then writing into the master device. So we're reading from a network terminal, writing into a master device, and then letting the process itself, the login shell, be able to read out of the slave. Remember, telnetd is running as root. So the login is running as user, and we've got to have some interface to protect the two. And that's what the master-slave device interface is for. And that just continues on with that story. Now there's also something else going on with terminal device buffering, and that's called raw versus canonical. Raw has the backslashes, the backspaces, things like that already in it, whereas the canonical data is the stuff that's already had those control characters taken out and processed. That's essentially the difference. There's a SAR